Hello everyone, and good evening to your second session, I believe, on as a tutorial on for this course, that is Introduction to Biostatistics and Experimental Design. I am assuming you have finished. Before we start off, let's establish some ground rules. First, if you wish to speak, it'll be nice if you can switch on your camera and speak. Before speaking, introduce yourself, your name, where you're from, and probably a line on why you want to do this course, why you've joined this course. And also, since I'll be switching screens while teaching, I won't be able to see if anyone raises your hands to ask a doubt. Okay, so please feel free to interrupt. It's a small class, I hope. So it is okay to just speak up. Okay, just yeah. If you have a doubt, just speak up and introduce yourself first, and then probably go on to ask your questions. Okay, is that all right? Okay, so also it'll be nice if you interacted as much as possible so that both you and I can gain the maximum out of this. Uh, I mean, it's better if there is interaction and yeah, all can learn together. Okay. Okay, great. What we'll do today is just go over some problem questions which are pertinent to the classes you have uh, you have gone through in the last 2 or 3 weeks. Okay. We'll be doing something that was done in previous years. I won't be doing your assignment as such. Okay. But we'll be tackling problems that are sort of uh, sort of relevant to the course you're doing. Okay. So the first 2 weeks mainly dealt with probability distributions, and things like that. Okay, and something with hypothesis testing. 1 second, can I'll just put myself. Yeah. Okay. So is that all right? We'll go on to doing some problem questions, and you can ask me doubts uh, as we go through the problem sets. Anything to do with the course so far, you can ask me questions on those. Okay. So the first question is, given two drugs A and B, A has a success rate of 75% and B has a success rate of 55%. What is the probability that both drugs fail? Okay. Or what is the probability in percentage that both drugs fail? Anyone that has some kind of approach to this question? Yeah, you can speak up.
Sir, your screen is not visible, sir.
Oh, okay. Oh, sorry. I'll just share my screen. So sorry for that. Uh, yeah. So can you see my screen now? Uh,
Yes, sir, it is visible.
yeah. So given that drug A has a success rate of 75% and drug B of 55%, what is the probability that both will fail? Eh, Anyone? Okay, maybe I'll start off with this question, and maybe others can join in for later ones. So I have just some presentation sort of thing ready. Yeah. Oh, this was a separate. Maybe we'll do. Is your problem set one done? I don't know. Is it like done and past its due date? We can do that.
Sir, actually, week one assignment has been over, sir.
Okay. Okay. No, it's okay. We'll do this problem set. So, given that probability that drug A works, uh, what is the probability of it not working? The probability of it working is 75%, right? So the probability of it not working is 25%, which is 0.25. Okay, and probability of drug B working is 55%. Okay, if you can go back to the question, yeah, it's 55%. So the probability of it failing is 45%. So the probability of both drugs failing is basically both drugs should not work at all, which is given by this thing, that is this formula, that is probability of drug A not working and probability of drug B not working. The probability of A not working is 0.5, 0.25, and probability of B not working is 0.45. And if you multiply both, you get something like 0.1125, which is 11.25%. Yeah. So do you know how this we arrived at this answer and why we have done a multiplication here? So we do this multiplication when we have an AND condition in our problem set. That is, and meaning that both drug A and drug B don't work, which is why we need to multiply. If we had a probability of drug A or drug B not working, it we have approached it in a different manner. Okay. So everyone got that? Can I hear a yes or a no? Or if someone hasn't got that, please let me know. Has someone got it? Like, got the approach to the question?
Yes, sir. Got the understood.
Yeah, ma'am, can you please introduce yourself to the class so that we all know something about you, and yeah, everyone knows something about each other. It makes the class a little more lively. Yeah.
Right, sir. Right, sir. My name is Preeti. I'm from Hyderabad, and I have joined this course to have a better understanding about biostatistics. It's useful for my career.
Okay. What background do you have? What are you? Sorry.
Pharmaceutical industry.
Okay, you're from pharmaceutical industry. Okay. So yeah, I think this will be very relevant to you, right? this sort of, yeah. Okay. The next question is, we are conducting a clinical trial for a viral load lowering drug. So basically a drug that lowers your viral load, the amount of virus in your body in some sense. In addition to the test group basically means on which the group, the set of individuals to whom you give the drug. Okay, what other groups should be present? Okay, anyone with what other groups apart from the group to which you give the drug that you need to test should be there in your group, study design? Anyone?
Option C, sir.
Sorry, I heard someone unmute. You can get back and
The third option.
third option. There should not be a control group who are given the drug, but the placebo group.
No, sir. There should be a control group as well as placebo group. Yes, sir.
Okay, so fourth option. Yeah, do you
Yes,
see
sir.
why? Can you introduce yourself to the whole group, your name and your background?
Yes, sir. Myself, Dinesh. I'm from Nashik and TYB Farm. I'm studying in TYB Farm.
Sorry, I didn't get the last bit. You're from Nashik and?
Third year, Bachelor of Pharmacy.
Okay, pharmaceutical. Okay, great. A lot of people from pharmacy then. Nice. So yeah, the answer to that is you need to have a control group, that is to whom you don't give the drug. Okay, and also a placebo group to whom you give something which is not a drug. It's nothing. Placebo means like it's just in olden days it used to be just a block of chalk. Okay, nothing. So yeah, you need to give a control group to actually ascertain. So why do you need to give a control group first? You need to give a control group to ascertain whether your drug has any effect. Okay. So a control group is you don't give anything to them, but they do have some viral load. Okay. And you want to, if you compare this control group with the group which has a viral load and you give the drug to them, you will know how effective your drug is. Also, you need to give a placebo group So just to as a control to just giving the act of actually giving that medicine. Now, medicines are given in sort of pills and things like that. You need to replicate just that because sometimes these things can have a psychiatric effect also. That is, people react differently just because of the fact that they are given something. Okay, it could be, it could not be a drug at all. Okay, but just the act of giving something that looks like a drug itself can have an effect. Okay, and the drug that you give comes in sort of pills or something. So just to control for that effect, you have a placebo group. Okay, it you can also use this to determine the effectiveness of your drug. So comparing your placebo group again to your group where you actually administered your drug also gives you the efficacy of your drug. Okay, so the giving placebo is just like replicating the manner in which you give the drug to the individuals. So that is why you need a placebo group also. Sometimes it's given through pills, sometimes it's given through IV fluid and things like that. Okay, is that clear to everyone? Can I hear a yes or a no?
Yes, sir.
Okay. Let's go on to the third question. Given that we are testing if drug A is more effective than drug B, which of these statements are correct? So your H naught here is your null hypothesis that both drug A and drug B are the same. HA is your alternate hypothesis, and this could be any of these things. So which do you think is the correct statement in these four, among these four, as which sort of tells you that drug A is more effective than drug B?
Option C.
Yeah? C.
C.
Someone said C. May I know your name, please? Is it Dinesh again?
Sir, I am Bishal Chaudhary. I am from microbiology background.
Okay.
Third option is correct, I think.
Yes. So your null hypothesis is always like what is the bare minimum that you know or you don't know about the system, and that is that the simplest sort of hypothesis that you can make for testing, and that is drug A is equal to drug B. The efficacy is the same. And you need to compare this to an alternate hypothesis that is drug A is greater than the efficacy of drug A is greater than drug B. So these are your set of hypotheses. Your null is basically both are similar, and your alternate is that drug A is more effective. And when you compare HA to H naught, you will determine whether drug A is more effective than drug B. Okay. So your null hypothesis basically tells you some benchmark against which you compare your experimental results to. Your experiment here is to test whether drug B A is greater than drug B. So that's your alternate, and you will compare it with your null hypothesis, that is drug A equals drug B efficacy. Okay. Okay. The next question is probability of congenital blindness is 1 out of 8. What is the probability that 3 out of 10 persons in a family often have that disease? Anyone? We'll go step by step in this, but anyone with the first step? So, what is the probability of congenital blindness?
So
What is?
basically, we have to use binomial distribution.
Yes. Okay, we'll do that step by step. So, the first thing you need to calculate the probability of congenital blindness, that is 1 out of 8, which is nothing but 1 out of 8 is how much? 0.125. Okay, and your number is 10. Sorry, the number of individuals, your sample, that is 10 individuals. I need to calculate how many, what is the probability that 3 of them have this disease. So to do that, you directly apply the binomial formula, which is n choose 3. 3 because n here is 10 individuals. Choose 3 is basically you are choosing 3 individuals to have that disease, and then probability of not being blind is so the what is that is n probability of not being blind is how much? 0.125 1 minus 0.125, that is 0.875 into number of people raised to the power number of people that are healthy, that is given by n minus 3, into probability of being blind, that is 0.125 raised to the power 3. Why raised to the power 3? Because you want to uh, ascertain the probability that 3 people are actually blind. Okay. So did everyone get this formula? This is the main formula. N choose 3, that is choosing 3 individuals that are not blind, that are actually blind, sorry, into probability of not being blind raised to the power 7 into probability of being blind raised to the power 3. Did everyone get that? This is like direct binomial formula application. And note that when you're doing these things, the assumption is that probability of being blind of one person is independent of the other person. That is, one person being blind does not affect the probability of the other person being blind. So that is a very basic assumption in Bernoulli's formula. That is, every trial is independent of the other trial. Okay, otherwise you cannot apply this formula. So if you calculate that, you will get something that is, if you calculate this term, n choose 3 is given by n factorial, n minus 3 factorial into 3 factorial. You will find this on the net. Okay. So if you calculate this entire term, you will get something that is given in the answer for this. Now, where is the answer? I haven't done the calculation, but yeah. Yeah. Is everyone okay with the approach? And does anyone have questions? Yeah.
Yeah, okay.
Sorry.
Okay, I understood what it is.
Yeah. Who's this? Can you introduce yourself?
I've already introduced
Okay,
myself.
Preeti. Okay, Preeti. So I can't see the screen where I'm hosting the meeting because I'm switching screens. So yeah. So sorry for that. Okay. Let's go on to the next question. The probability of a birth defect is, no, okay, it's this. A drug is being tested for curing ovarian cancer, and the mortality rate while this drug is being tested is 9%. What is the minimum number of patients required to demonstrate the efficacy of the drug at 95% confidence? Do you understand this question, everyone? Can someone explain the question to me? Anyone? Can you explain the question, what 95% confidence interval confidence is and things like that? Anyone, please? It'll be nice. You speak up. Anyone? Okay, maybe I'll explain the question. So you need to calculate the minimum number of people to demonstrate efficiency of the completely curative drug. So what you have to do, what the question is asking is, what are the minimum number of people you need to test so that you get a confidence that this drug will not kill people. Okay. And the drug has a mortality rate of 9%. Okay. It kills 9% of the people. Okay. You need to show that, okay, if with a mortality of 9%, how many minimum number of patients you need to test the drug on to show that the drug is completely curative, that is, it cures the disease. Okay. So to do that, you need to first calculate the probability of mortality, which is 0.09, it's 9%. What is the probability of survival? It cures 91 people of the thing. Okay. And it does not cure 9%. Okay. To prove efficacy, sorry, to prove efficacy, you need to show that what is the minimum number of people you need to test for 0 persons dying. Okay. Which is nothing but n at 95% confidence interval. Okay. So that is given by NC0 into NC0 is basically you don't want anyone to die. Okay. So that's NC0 amounts to how much? 1. Okay. Because it's given by n factorial divided by n factorial, which is 1. Okay. Into probability of survival. So survival, everyone should survive. All the n number of people should survive. And p, that is p, probability of mortality, is raised to 0. If you simplify this entire thing, you get something as 0.91. It is just this probability of survival raised to the power n. Okay, and this should be lesser than 0.055. Okay, that is 95% of the, with that, which basically means 95% confidence. That is, it's only 0.05% of the people at the max should die. Okay, of all the people that you test. Okay, not test, when you deploy the drug, not more than 5% of the people should die. Okay, so the basically this drug should work on 95% or more of the people. So when you have to calculate this expression. Okay, and then how do you do this? You convert left and right to the log. So you know basic log properties, right? So when I take log on both sides, log of 0.91 power n can be written as n log 0.91, and this should be less than log 0.05. And when you find the log of 0.91, it's this, log of 0.05 is this, and when you simplify, you get n less than 32. Sorry, n greater than 32. Okay, n comes aside, this 1.3 goes that side, and when you take the denominator, when you simplify this, you get n greater than 32. Is this okay? It's some math, but you have to look up log properties. The important part is this: 0.91 raised to the power n should be less than 0.05. Is that okay? Is that understood? It's slightly complicated question.
Yes, sir.
Yeah. From this, you have to just apply math, elementary math, some log properties. Okay. Great. The next is, I found this, oh, this one. The probability of birth defect is 0.11. What is the probability that no one in a family of 15 people will have that birth defect? Okay. And you have to use Poisson distribution for this. Okay. Now for this, again, so I'm assuming you know a little bit about how Poisson distribution looks and things like that. Everyone knows a formula for Poisson distribution. Can someone tell me what the thing is? It's given here. So forget this less than or equal to 0, but a Poisson distribution for any given x is given by e power minus lambda. Lambda is a rate at which some event happens, into lambda power x. Okay, x could be whatever your interest in, your random variable of interest, divided by x factorial. Okay, now the question asks, what is the probability that no one in a family dies? So basically s should be less, x is 0 here. Okay, so everything is raised to the power 0. In a family of 15 have that birth defect. Okay, so first you need to calculate the lambda. Lambda is given by 15 into 0.11. Okay, that's the rate. So probability into number of people gives you the rate at which this event occurs per whatever person or something like that. Okay, and then you substitute lambda in this formula, that is e power minus lambda into lambda power 0 divided by 0 factorial, and when you do that you get 0.19 as the answer. Is that okay? Did everyone get that? Yeah. So the important part is to get lambda, which is basically number of people into your uh, probability that it infects one person also. Yeah, that's rate is 1.65. So every 1.65 out of 15 people get affected. Okay, that's the rate. Now you need to calculate what is the probability that no one gets affected. among these 15 people. Yeah. Did everyone get that? Can I hear a yes or a no?
Yes, sir.
Okay, great. Then there is this question is actually a little stupid, but we'll do that nonetheless.
Yeah.
It says,
Sir,
yeah, someone had a
sir,
doubt. Someone had a doubt?
my name is Anandakrishnan. I'm doing my post graduation in population sciences.
Okay.
Sir, actually, I have a doubt that whether we can use the binomial distribution here, or why we are because the question itself saying that about using the Poisson distribution.
Yeah. So I think they want us to use the Poisson distribution. I don't know why. I would have chosen the binomial distribution. And I would have done it similar. So in all practical purposes, I think you need to use the binomial like we did the previous question, this question.
Okay.
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 So there it will be, what will it be there? It will just be n choose 0 into probability of not having that bird defect, which is 0.91. Sorry, not bird, sorry. This one, right? Yeah, 0.91 raised to the power 15 into having that thing that's 0.11 raised to the power 0. Yeah?
Yes, sir. I have a doubt that these question have the same characters like these are non independent events and
Yes,
the
yes,
small space,
yes.
everything that of binomial
Yes,
distribution
yes,
here.
yes, exactly. Yeah. So, yeah, that is why I don't think it's advisable to use poison. They have asked it, I don't know why. I would have, in all practical purposes, used a Bernoulli's uh, trial estimation. Yeah,
Okay.
and done a
Thank you, sir.
binomial. Okay. The next question is, given that you count 1650 red blood cells per 1 ml of blood, what is the 95% lower limit for the patient's true blood cell count? So here you have to use the Poisson. Why? Because you're assuming counts, right? Counts have a Poisson distribution. It's implicit here. Okay. And in a Poisson, you know that the mean equals variance. Okay. Does everyone follow that? So here the mean, which is lambda, is 1650. Okay. And you basically just need to use that to calculate 95% confidence intervals. And to calculate 95% confidence intervals, you need to use this formula. That is, okay. I sort of have missed that. We can do it. Where is that? I sort of had that slide. Okay, we'll do that. We'll do that on a fresh slide. So for a Poisson, your lambda is equal to the mean, which is equal to the variance. Okay, and the formula for getting 95% confidence interval is, I think it's a z value, which is 1.96. You can look this up, okay? Into standard deviation, which is variance, square root of variance, SQRT of whatever variance, divided by root n, is it? Yeah, and here this sample is just one sample, so it's square root of 1. Okay, square root of n, I'll write here. Okay, this entire thing. So everyone got this formula, and then this is the 95% confidence interval. Okay, and then you need to just, yeah, calculate if for lower 95% confidence, you need to subtract for lower CI, lower 95% CI, you need to do mean minus this, whatever. Okay, and for the upper CI, you need to just add that. This is the formula. So let's calculate. So 1.96 into square root of